The race for Mars. What happens when humanity becomes interplanetary? A permanent human settlement on Mars would fundamentally alter our species' future and reshape geopolitics on Earth. That moment is closer than most people realize. February 2024 brought SpaceX's Starship to orbit for the third time, demonstrating controlled re-entry and splashdown. The world's most powerful rocket completed nearly a full mission profile, proving the technology that could carry humans to Mars within the next decade. 1 month later, China announced plans for their Long March 9 super heavy lift rocket capable of matching Starship's payload capacity by 2030. All of this unfolds while NASA's Artemis program prepares to return humans to the moon by 2026, where India has already landed near the lunar South Pole and where China plans to construct an international research station by 2035. The stakes extend beyond national pride. Whoever establishes the first permanent Mars colony could claim access to rare minerals worth quintillions of dollars, define the legal framework for off-world settlement, and secure humanity's survival as a multi-planetary species. So what if the race to Mars becomes the new space race of the 21st century? The new space powers. SpaceX now commands the most capable launch system on Earth, with Starship standing 121 meters tall and generating 16.7 million pounds of thrust, nearly double the Saturn V's 7.6 million. The Falcon 9 has completed over 380 successful launches, with 350 booster landings and reuse rates exceeding 20 flights per booster. By 2025, SpaceX launched every 3 days on average, while the entire Chinese space program managed roughly 70 launches annually. But China's catching up fast. Their commercial space sector exploded from essentially zero in 2015 to over 400 companies by 2024. Landspace became the first private Chinese company to reach orbit with a methane-fueled rocket in July 2023, matching SpaceX's Raptor engine technology. The Long March 9, scheduled for first flight in 2030, will deliver 150 tons to low Earth orbit compared to Starship's planned 150 to 250 tons when fully operational. China landed the Zhurong rover on Mars in May 2021, becoming only the second nation to successfully operate a rover on the Red Planet. Their Tianwen-1 mission carried an orbiter, lander, and rover all at once, a technical achievement NASA took 3 separate missions to accomplish. November 2024 brought the launch of Tianwen-2, targeting a near-Earth asteroid for sample return by 2026, followed by Tianwen-3, an ambitious Mars sample return mission planned for 2028, 2 years ahead of NASA and ESA's joint effort. None of that matters as much as infrastructure. China completed their Tiangong space station in November 2022 with 3 modules supporting permanent crews of 3 astronauts. They've hosted 12 crew rotations since 2021 and announced plans to expand to 6 modules by 2030, potentially surpassing the International Space Station size. Meanwhile, NASA faces ISS deorbiting in 2030 with no government-owned replacement, relying instead on commercial stations from Axiom Space and Blue Origin that have yet to launch. The geography of Mars. Mars measures 6,779 kilometers in diameter, about half Earth's size, with surface area roughly equal to all of Earth's land combined. That's 144.8 million square kilometers of territory, equivalent to claiming 28 continents the size of Asia. The planet rotates every 24 hours and 37 minutes, remarkably similar to Earth, but orbits the Sun every 687 Earth days, with seasons lasting nearly twice as long. Temperature swings define Martian survival. Summer at the equator reaches a comfortable 20 degrees Celsius during the day, but plummets to minus 73 degrees at night. Winter at the poles drops to minus 125 degrees Celsius. The atmosphere sits at just 0.6% of Earth's pressure, composed of 95% carbon dioxide, making every human habitat a pressurized vessel one puncture away from catastrophe. But Mars offers resources. The north and south polar ice caps contain enough water ice to cover the planet's entire surface in liquid water 35 meters deep if melted. Perchlorate salts in Martian soil, while toxic to humans, can be processed into rocket fuel. Iron oxide gives Mars its red color and represents massive deposits accessible through surface mining. The Jezero crater, where NASA's Perseverance rover operates, shows evidence of ancient river deltas and clay minerals that form only in the presence of long-lasting water. Olympus Mons towers 21.9 kilometers high, nearly nearly 3 times the height of Mount Everest and stretches 600 kilometers across its base. Valles Marineris, a canyon system running 4,000 kilometers long and 7 kilometers deep, dwarfs the Grand Canyon by a factor of 10. These features aren't just geological curiosities. They represent natural shelters offering radiation protection and potential subsurface ice deposits. SpaceX selected a landing site near the Martian equator, optimizing for solar power and moderate temperature. China announced interest in Utopia Planitia, a vast plain in the northern hemisphere where subsurface ice sits just meters below the surface. NASA focuses on regions with confirmed water ice at mid-latitude. Every agency targets different real estate, and no international treaty clearly defines who owns what once boots touch the ground. The technology gap. Getting to Mars requires solving velocity. Earth's gravity well demands 11.2 kilometers per second to escape. Mars transfer orbits need another 3.6 kilometers per second. Total delta V requirements reach approximately 15 kilometers per second, consuming massive amounts of propellant. Traditional chemical rockets burn through fuel at extraordinary rate, forcing missions to carry multiple times their payload weight in propellant alone. SpaceX's solution involves in-space refueling. A single Starship can't reach Mars on one tank. The plan requires launching 8 to 10 tanker Starships to refuel one Mars-bound vehicle in Earth orbit, transferring roughly 1,200 tons of liquid methane and oxygen. Each refueling mission depends on perfect execution, and any failure leaves the crew stranded in orbit or forces mission abort. China pursues nuclear thermal propulsion, heating hydrogen propellant with a nuclear reactor instead of chemical combustion. This approach theoretically doubles efficiency and cuts Mars transit time from 6 to 9 months down to 3 to 4 months, reducing crew radiation exposure and psychological strain. Their space-based nuclear reactor test began in 2023 with operational systems targeted for 2030. NASA's Draco program, partnered with DARPA, aims to demonstrate nuclear thermal propulsion by 2027, but faces regulatory hurdles and budget constraints. Radiation remains the silent killer. Mars missions expose crews to 0.3 sieverts during the journey and 0.2 sieverts annually on the surface, totaling roughly 0.7 sievert for a 2-year mission. That's approaching the 1 sievert career limit NASA sets for astronauts and increases cancer risk by approximately 5%. Solar particle events, unpredictable bursts of radiation from the sun, can deliver lethal doses in hours without proper shielding. Landing presents another challenge. Mars's thin atmosphere provides just enough resistance to heat spacecraft during entry, but not enough for parachutes alone to slow multi-ton vehicles to safe landing speed. SpaceX plans supersonic retropropulsion, firing engines while still traveling faster than sound to brake against the thin atmosphere. They've tested this successfully with Falcon 9 boosters on Earth, but never with a vehicle carrying 100 tons of cargo and crew arriving from interplanetary space at 7.5 kilometers per second. The timeline to Mars. Elon Musk has consistently projected the first crewed Mars landing in the late 2020s, most recently targeting 2029 for SpaceX's first human mission. NASA's Mars campaign operates on a more conservative timeline, planning crewed missions in the late 2030s or early 2040s following extensive lunar infrastructure development. China hasn't announced specific dates for crewed Mars missions, but their leaked roadmap suggests the late 2030s. The Artemis program serves as the foundation. Artemis 2 will fly 4 astronauts around the moon in September 2025, followed by Artemis 3 landing near the lunar South Pole in 2026 or 2027. Subsequent missions will construct the Lunar Gateway, a small space station in lunar orbit serving as a staging point for surface operations and deep space missions. NASA considers this essential practice for Mars mission, testing life support, habitats, and resource extraction in a location just 3 days from Earth instead of 7 months. SpaceX takes a different approach. While participating in Artemis through the Human Landing System contract, they're developing Mars architecture independently. Starship's first uncrewed Mars missions could launch as early as 2026 during the next favorable launch window. These would deliver cargo, test landing systems, and pre-positioned supply. Crewed missions would follow in 2028 or 2029 if everything succeeds perfectly, an ambitious timeline most experts consider unlikely. China's strategy emphasizes methodical progression. Their lunar program advances toward a crewed moon landing around 2030, followed by lunar base construction through the 2030s. Mars missions would likely begin after proving technologies at the moon, suggesting the late 2030s or early 2040s for their first crewed attempt. However, geopolitical competition could accelerate these plans if SpaceX or NASA appears close to success. Launch windows dictate the schedule. Earth and Mars align favorably every 26 months when the planet's orbit bring them relatively close together, creating brief opportunities for efficient transfers. Miss one window and the mission delays 2 years minimum. Every window represents a chance to leap ahead or fall behind, intensifying the competitive pressure. The cost of failure. Building a Mars colony requires extraordinary resources. SpaceX estimates their program needs roughly $10 billion to reach the first crewed landing, with total costs potentially exceeding $100 billion for a self-sustaining settlement of 1,000 people. NASA's Mars campaign budget remains classified, but likely measures in the hundreds of billions when accounting for Artemis infrastructure, Mars-specific hardware, and decades of operation. China's space budget reached approximately $14 billion in 2024 compared to NASA's $25 billion. However, China's space program operates with state-controlled supply chains and labor costs roughly one-third of Western equivalent, stretching their budget significantly further. Analysts estimate China could match NASA's Mars capabilities at half the dollar cost through industrial efficiency and centralized planning. Human costs hit harder than money. The Columbia Accident Investigation Board found that NASA's acceptable risk threshold for crew loss sits at 1 in 270 missions. Mars missions carry far higher danger. The Center for Strategic and International Studies assessed Mars mission risks at approximately 1 in 10 for total crew loss during early missions, dropping to perhaps 1 in 50 once systems mature. That means the first few crews face roughly a 10% chance of never returning home. Psychological factors threaten mission success as much as engineering failure. The Mars 500 simulation, which isolated 6 volunteers for 520 days to simulate a Mars mission, documented severe depression, motivation loss, and interpersonal conflict. Crew members developed sedentary behavior, reduced activity levels, and disrupted sleep cycles despite perfect safety and health. Actual Mars missions add radiation, real danger, communication delays up to 22 minutes each way, and no possibility of rescue or evacuation. Medical emergencies become death sentences. A burst appendix, easily treated on Earth, turns lethal on Mars. Broken bones could heal improperly without proper imaging and orthopedic equipment. Dental infections could progress to sepsis. The limited medical supplies and equipment would turn routine problems into mission-ending or life-ending crises. Every crew member needs cross-training in emergency medicine, but a biologist trained in first aid isn't a trauma surgeon. The legal vacuum. The Outer Space Treaty of 1967 prohibits nations from claiming sovereignty over celestial bodies, stating outer space, including the moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. 114 countries signed this treaty, including the United States, Russia, and China. But the treaty doesn't address resource extraction, commercial activities, or settlement. Can SpaceX claim mining rights to Martian regolith? Can China declare a safety zone around their base where others can't land? Can settlers vote to establish their own government independent of Earth nations? None of these questions have clear legal answers. The Artemis Accords, signed by 47 nations as of January 2025, attempt to fill these gaps. The accords establish safety zones around lunar and Martian operations, allow resource extraction, and create frameworks for preventing harmful interference. Notably, China and Russia refused to sign, calling the accords an attempt by the United States to impose unilateral rules on space activity. This sets up competing legal framework. Artemis Accord signatories, including the United States, Japan, India, and European nations, operate under one set of rules. China, Russia, and their partners operate under different principles, emphasizing UN oversight and collective decision-making. When a Chinese rover drives within kilometers of an American base, which rules apply? When both nations claim the same ice deposit, who has priority? The 1979 Moon Agreement attempted to prevent exactly this scenario by declaring celestial resources the common heritage of mankind, requiring international sharing and UN oversight. Only 17 nations signed it, and none of the major spacefaring powers ratified the treaty. Without enforcement mechanisms or broad acceptance, the Moon Agreement exists as an idealistic document with no practical authority. Private companies complicate matters further. SpaceX, a U.S. corporation, operates under American law, but what jurisdiction governs actions on Mars? If a SpaceX employee commits a crime on Mars, which courts prosecute? If a structure built by a Chinese company on Mars fails and kills residents from multiple nations, who investigates and assigns liability? Current law provides no answer. The economic prize. Mars potentially holds resource wealth beyond comprehension. A single metallic asteroid, 16 Psyche, contains an estimated $10 quintillion worth of iron, nickel, and precious metal. Mars's Hellas Basin, a massive impact crater, likely contains similar concentrated deposits of heavy elements. Even conservative estimates suggest trillions of dollars in accessible minerals once extraction infrastructure develops. Rare earth elements critical for electronics, batteries, and advanced manufacturing exist in Martian regolith at concentrations potentially higher than Earth's easily accessible deposit. Neodymium, essential for powerful magnets in wind turbines and electric motors, remains scarce and expensive on Earth. Platinum group metals, used in catalytic converters and fuel cells, command prices exceeding $30,000 per kilogram. Mars could supply these materials once launch costs drop sufficiently. But the real value lies in becoming Earth independent. Every kilogram launched from Earth to Mars costs approximately $100,000 with current technology, even with SpaceX's optimistic projections of future Starship economics. Manufacturing propellant, construction materials, and life support consumables on Mars eliminates this cost for Mars-based operation. A self-sufficient Mars colony could export manufactured goods, produce fuel for missions to the asteroid belt, and serve as a hub for outer solar system exploration. Intellectual property generated on Mars could prove even more valuable. Material science conducted in 0.38 g gravity might discover new alloys impossible to manufacture on Earth. Pharmaceutical research in Mars's unique radiation environment could yield novel treatment. Genetic research freed from Earth's regulatory frameworks could advance decades ahead of terrestrial science, raising ethical questions but generating potentially enormous profit. Tourism represents another revenue stream. Dennis Tito paid $20 million for 8 days aboard the International Space Station in 2001. Adjusted for inflation and the dramatically higher cost and risk of Mars travel, a ticket to Mars might command $50 to $100 million per person initially. SpaceX's stated goal of reducing this to under $500,000 per person would open Mars to millions of Earth's wealthiest citizens, creating an entirely new luxury market. The strategic implications. Whoever controls Mars infrastructure controls access to the outer solar system. Launching from Mars requires just 5 kilometers per second of delta V to escape compared to Earth's 11.2 kilometers per second. Mars serves as a natural staging point for asteroid mining, missions to Jupiter's moons, and exploration of the outer planet. The nation or entity dominating Mars effectively controls humanity's expansion into the solar system. Military implications remain speculative but concerning. The Outer Space Treaty prohibits weapons of mass destruction in space, but doesn't address conventional weapons or dual-use technology. A spacecraft capable of changing an asteroid's orbit for mining could redirect that asteroid toward Earth. A Mars base with significant industrial capacity could manufacture kinetic impactors and launch them toward Earth at speeds impossible to intercept with current missile defense systems. Communication delays range from 3 to 22 minutes one way, depending on planetary position. This makes real-time Earth control of Mars operations impossible. Any Mars settlement must operate with significant autonomy, making decisions locally and informing Earth after the fact. This autonomy inevitably leads toward political independence as the settlement grows and Earth's ability to exert control diminishes with distance. China's strategy emphasizes dual-use technology and civil-military fusion, where advances in civilian space programs directly enhance military capabilities. Their space station hosts experiments improving satellite technology, orbital rendezvous, and long-duration spaceflight, all applicable to military operations. A Chinese Mars base would similarly advance capabilities relevant to Earth orbit military applications while establishing presence beyond any rival's reach. The United States maintains technological leads in several areas: reusable rockets, deep space communication networks, and planetary science. But China's industrial capacity and centralized decision-making enable faster mobilization of resources toward strategic goals. The question isn't whether China can match American capabilities, but how quickly they can close the gaps that matter most. The point of no return. The first permanent Mars settlement, regardless of which flag it flies, marks the point where humanity becomes truly interplanetary. This changes our species fundamentally. We stop being creatures evolved for one planet and become a civilization spanning multiple worlds. That transition carries profound implications. A Mars colony requires complete self-sufficiency within 10 to 20 years. The logistics of supplying a Mars base from Earth become economically unsustainable as the settlement grows. Every kilogram of food, water, and equipment shipped from Earth costs millions in launch expenses. The colony must manufacture its own food through greenhouses, extract water from ice deposits, produce propellant from Martian atmosphere and water, and construct habitats from local material. Population size determines survival probability. Studies suggest a minimum viable population of 110 people to maintain genetic diversity and essential skills, with 500 to 1,000 providing reasonable margins for accidents and losses. Each person requires approximately 50 tons of equipment and supplies for the first year, suggesting initial cargo missions totaling 5,000 to 50,000 tons before the first humans arrive. The first children born on Mars will be Martian, not humans visiting another world. They'll develop in 0.38 g gravity, potentially growing taller with weaker bones and muscle. Whether they could ever safely visit Earth's 1G environment remains unknown. These children represent the first generation of humanity permanently separated from Earth by biology, not just distant. Political independence becomes inevitable. Mars colonists, making life and death decisions daily, won't accept governance by officials on Earth who don't understand Martian conditions and whose commands arrive minutes or hours late. The American Revolution occurred partly because colonists separated by a 6-week ocean voyage from Britain developed distinct interests and rejected distant rule. Mars settlers face separations of 7 months and communication delays measured in minutes, making Earth governance practically impossible.